One of the earliest concepts in thermal physics that causes confusion is the difference between heat and temperature. In our mind, heat and temperature seem to mean the same thing. Physically, this isn't true, though. Heat is a form of energy transferred from hot substances to cold ones. Temperature is a measurement of average kinetic energy of the molecules in a system. You'll soon see these must be different, as there are times when adding heat to a system doesn't likewise increase the temperature. In this lesson, we're going to show how heat affects temperature and phase changes in substances. Phase changes happen when a substance goes from a solid to a liquid to a gas and vice versa. We'll work through an example problem that deals with heating up substances and learn how to read heating curves. We're going to see how heat and temperature interact by calculating how much heat it takes to take 50 grams of negative 20 degree Fahrenheit ice and turn it into 80 degrees Fahrenheit water. In order to do this, we're going to have to use two different energy formulas, one for specific heat and one for latent heat. The specific heat formula that you can see on your screen tells us how much added heat, represented by Q, it takes to change a substance's temperature. Here, M is mass, delta T is change in temperature, and C is specific heat. The specific heat is the amount of heat it takes to raise a substance's temperature by 1 degree Celsius. While the specific heat formula tells us how much heat it takes to raise a substance's temperature, it does not tell us how much heat it takes to change a substance's phase. For that, we use the latent heat formula, Q equals mL. Latent heat, or L, is the heat required to change a substance's phase per unit mass. There are two different types of latent heat: latent heat of fusion and latent heat of vaporization. The former deals with the substance's change between solid and liquid, and the latter the change between liquid and gas. Specific and latent heat are unique to each substance. For our example, water has the specific and latent heat values that you can see listed on your screen as we speak. J stands for joules, which are units of energy measurement. In this case, we see JG, or joules per gram, which refers to units of heat energy dispersed over the mass of an object. We use the specific and latent heat equations together when a substance's raise in temperature brings it from one phase to another. In our example, the total heat added, QTOT, would be how much heat it takes to raise the ice's temperature to the point where it melts, QI, plus how much heat it takes to change the ice to water, QITW, plus how much heat it takes to raise the water's temperature, QW, to 80 degrees Fahrenheit. Before we plug in all the information for our problem, we need to do one more thing. We need to convert our temperature from Fahrenheit to Celsius. In order to do this conversion, we use the following formula. C equals F minus 32 times 5 over 9. For this problem, we need to convert our starting temperature of negative 20 degrees Fahrenheit and our ending temperature of 80 degrees Fahrenheit. C equals negative 20 minus 32 times 5 over 9 equals negative 29 degrees Celsius. C equals 80 minus 32 times 5 over 9 equals 27 degrees Celsius. Now we use all the information we've been given in this section to solve our problem. Q total equals 50 grams times 2.01 joules per gram degrees Celsius times 0 degrees Celsius minus negative 29 degrees Celsius plus 50 grams times 334 joules per gram plus 50 grams times 4.18 joules per gram degrees Celsius times 27 degrees Celsius minus 0 degrees Celsius. Q total equals 2,915 joules plus 16,700 joules plus 5,643 joules. Q total equals 25,258 joules. Finally, let's make a quick note about how our temperature intervals for delta T, or the final temperature minus initial temperature, were chosen. These temperature intervals were chosen because above 0 degrees Celsius, ice melts. So our heat added for ice can only be applied for negative 29 degrees Celsius to 0 degrees Celsius, and our heat added for water can only be applied for 0 degrees Celsius to 27 degrees Celsius. In the previous sections, we got into the nitty-gritty of the relationship between heat and temperature by learning about specific and latent heat formulas. However, while focusing exclusively on formulas, it's easy to be left without an intuitive understanding of what exactly is going on. We can help forge a more intuitive understanding by looking at something called a heating curve. A heating curve shows the relationship between temperature and heat added. You can see in the diagram on your screen that the temperature of a substance goes up as more heat is added to it. You'll also notice that there are large portions of the graph that are horizontal lines. Here, heat is being added, but temperature isn't increasing. This happens because all the heat at this point is going into changing the phase of the substance instead of making it hotter. So the first horizontal segment represents the melting point, where the substance changes from solid to liquid, and the second horizontal segment represents the boiling point, where the substance changes from liquid to gas. Heat and temperature, while at first appearing similar, are actually two different concepts. Heat is energy that is transferred from a hot substance to a cold one, and temperature is a measure of the average kinetic energy of the molecules in a system. The two can be related together through the specific and latent heat equations. The specific heat equation is used for finding out how much heat is added, Q, to a substance during a change in temperature, delta T. Q equals mc delta T. Here, m is the substance's mass, and c is its specific heat, which tells us how much heat it takes to raise a substance's temperature by 1 degree Celsius. The latent heat equation is used for finding out how much heat is added to change a substance's phase, Q equals mL. Latent heat, or L, is the heat required to change a substance's phase per unit of mass. Latent heat can either be latent heat of fusion for changing between a solid and a liquid, or latent heat of vaporization for changing between a liquid and a gas. Finally, how heat and temperature interact in a substance can also be viewed graphically in something called a heating curve, which shows the relationship between temperature and heat added. It also shows the melting point, which is where a substance turns from a solid to a liquid, and the boiling point, which is where a substance turns from a liquid into a gas. As heat is added, temperature goes up, except during the horizontal parts of the curve, where all the heat is going into changing the substance's phase instead.